Then the third one is where we have our non-standard cell. So let's see how we would do that. So it tells you that you need to use the Nernst equation to calculate it. Still the zinc copper system. For this one, you're assuming a 0.5 molar for the copper, and there's still a 1 molar concentration for the zinc. Okay, so again, we want to use our Nernst equation here. Just type that over again. So the Nernst equation says that the E will be equal to the E standard, which we already calculated. That's our 1.1 minus RT. Missed something there. Divided by NF. That's very important. Then ln of Q. Okay, so we know most of the values in here. We already know this one. We do have to figure the N for this, though. So you could look at the half reactions, or you could just look at this balanced equation, and you can see that 2 electrons are transferred from zinc to copper. So the N here is 2 on that equation. And so it's the Q that we have to do a little bit of work on to get that. So let me just do that over here. I'm just going to do this over to the side to show you how you'd calculate Q. So it's products over reactants, which means the Q then would be equal to the product is the zinc, so that's our Zn2 plus solution, and I can't make that a superscript in here. Then it would be the concentration of copper 2 plus. And you don't have to square it or cube it or anything, because there's only a 1 in front of the copper. If there wasn't, then you'd have to do something in addition to that. So if we just plug the numbers in here, we're told that the zinc is equal to 1. It's 1 molar solution. And then that would be divided by copper concentration, which in this case is 0.5. 0.5 molar. So 1 divided by 0.5 is going to be equal to 2.0. Let's see, we'll give it 2, and that's unitless. So now we can finish our calculation. I'm just going to take this whole expression then and put the numbers in, but do it down here. Okay, starting over there, filling in the numbers. So our E equals the 1.10 that we already calculated, and that's in volts, minus 8.314, and that's units of joules per mole Kelvin, times the temperature, 298 Kelvin, then divided by NF. So that would be divided by 2, just an exact number there, times F, which is always the same. It's 96,485. The F, by the way, has units of joules per coulomb. Okay. So that's all in there. And then finally you have, that's all on the bottom. Then finally you have the natural log of Q, which in this case we already determined to be 2. Okay. So if we multiply all this stuff here, multiply everything from here over to there, let's see what we get. Start with the natural log. Okay, the natural log of 2 is 0.69, then times 8.314 times 298 divided by 2 divided by 96,485 equals, we get 0.009, and I'm just going to round that up to 0.01 because our standard potential only goes 2 places past the decimal, so it wouldn't make sense to do this to any more than that. So that rounds to 0.01 volts. So it's not a big change, but it is going to lower the voltage by a little bit. So our final answer here then, when we put it together with the 1.1, comes out to be 1.09 volts. Okay, so that's what would go in this. And the units would be volts. Okay, so you're going to be doing that with 4 different systems. Down to the next one. The next one is the lead copper. For this, you're also shown what the reaction is, which essentially tells you what the anode is. And so your lead is the anode, the copper is the cathode again. You go up and pull your values off of this table. So it's going to be 0.34 minus a negative 0.13, because the lead value is right there. 0.34 minus, so it's 0.34 plus 0.13, which is 0.47. So that's the 0.47 is what would go in the next answer here, and that would be volts. I won't put it in there. And then the anode and the cell described above, that's going to be your lead. Now for this one, this had a slightly different value for the concentration of the copper, but you'd again for this one use the Nernst equation again. Everything is 1 to 1, so really the only difference, and it's also 2 electrons again that are transferred. So the only difference is the standard potential that you get up here. You bring that one down, and your Q would be different this time as well, because it would be lead solution is 1. Your Q is going to end up being 1 over 0.1, so it's going to be a 10. So you have the natural log of 10 as the part of the expression there in the Nernst equation. Then down here you do the same thing for zinc and lead. Again, in the reaction I've identified the zinc as the anode, so there's no question in there. Do your Nernst equation again. This time it's 0.5, just like above. It's again 2 electrons. The one that's the most different is the last one you're going to be doing here, because that's with aluminum and copper. It's not different in terms of the standard potentials, because you still just use the 2 half cell potentials from above, and the copper again is your cathode, aluminum is your anode. So you calculate that one. But it's down here when you get to the Nernst equation here. This time the Q value is a little more complicated. So in your Nernst equation, Q is going to be equal to concentration of the aluminum 3 plus, because that's going to be your product solution. Squared. So that would be power of 2, and then that's going to be over the concentration of the copper solution, copper 2 plus, and that one's going to have to be cubed on the bottom. So the aluminum solution is a 1 here. So that's just 1.0 squared is still 1 over the the copper here was 0.1, 0, but the 0.1 on the bottom is what has to be cubed then. Okay, so that's going to be equal to 1 divided by 0.1 cubed is 0.001, which actually then gives you a value for Q of 1,000. Okay, so this time the Q is 1,000. You're going to be taking the natural log of 1,000 in the expression for in the nurse equation expression that has Q in it. Okay. So I think that's enough to give you a good start on that, and don't forget the extra credit part here, which is actually a lot of points on this one. Just click true and you get the 8-point extra credit, not extra credit, sorry, free points. And that's it.